want to start with two examples where we're just going to set up integrals. So the first one we can do is set up a triple integral to find the volume within the cylinder x squared plus y squared equals 1, below the plane z equals 4, and above the paraboloid z equals 1 minus x squared minus y squared. So I've already taken a minute to kind of sketch what this would look like. So the cylinder, we've got that cross-section of x squared plus y squared equals 1, and that's true for all z values. So it's really just that unit circle and then creating a cylinder up and down from it. So we can see that drawn on there. The plane z equals 4 obviously just is horizontal and cuts through when z equals 4. So I just kind of indicated that on the top here where we're going to cut that or that cylinder off at. And then we want to be above the paraboloid z equals 1 minus x squared minus y squared. So to picture that, I just kind of picked a few points. So like, well, what's z going to be when x and y are 0? It's going to be 1. And then what's it going to be when, like, we're at the point 0, 1, 0. So like at 1 on the y-axis, well, then z is going to be 0. So it's going to be this downward shaped parabola cross-section, so it's that paraboloid is shaped downward, starting at with kind of that vertex point at the 1 on the z-axis. And so the region that we're looking for here really is this chunk of the cylinder, except on the bottom we've kind of cut out a little bit of that domed part that is the shape of the paraboloid. So what we want to do is think about how to set this up. So we can think about what does z go from and to, and then what does x and y go from and to. So let's real quick here, I haven't drawn it yet, but let's draw the region R as well. So the region R is just in the xy plane. And if we can picture it on there, right, it's just where does it intersect the x and y axes, and it intersects at every point at 1. It does intersect the cylinder at that point, and it also intersects the xy plane at that point. So we just have a nice circular region with a radius of 1, so a nice unit circle for R, and we would be inside of that region. So this already starts to give us this idea that cylindrical coordinates are probably going to be pretty nice. When we look at all of those formulas, converting them into cylindrical seems pretty reasonable, and our regions all are fairly circular in nature, right? If I try and do this in cylindrical to find bounds for R and theta, well, R just goes from 0 to 1, and then we do a full rotation. So it goes 0 to 1, and then theta would go 0 to 2 pi. And then to think about, well, what z is doing is it goes from that paraboloid up to the plane. So z in rectangular coordinates, it's going from 1 minus x squared minus minus y squared to the plane, which is z equals 4. And so then if I convert that into cylindrical, it's pretty easy to do, because what we see is the lower bound is really just 1 minus the quantity x squared plus y squared, which is 1 minus r squared. And then if z is 4, if that's a constant, we can just leave it as 4. So it goes from 1 minus r squared up to 4. And so then when we put this in a triple integral, we're going to have volume. We could put, say, our theta bounds on the outside, so 0 to 2 pi. And then r goes from 0 to 1. Z goes from 1 minus r squared to 4. If it was in rectangular coordinates, we would just integrate 1, but then we would need to remember our change of coordinates factor, which for polar and cylindrical is an r, and then we would have dz, dr, d theta. Which if we think about, that's a fairly simple integral to do then, right? To integrate r dz first off is just leaving it, and then we can sub in those r bounds, and then we just have two constant integrals on the outside. So you can finish up that one if you want to find what that integral equals. but it seems a little easier than leaving this as z going from like 1 minus x squared minus y squared to 4, and then if we did it in rectangular to do the region R, we would have to go like from the negative square root to the positive square root of the unit circle, and then have x go from -1 to 1. So it saves us some of those nasty square roots to deal with. So it's an example where we decided to convert this to cylindrical. Now if we take a look at the next example says set up a triple integral to find the volume of x squared plus y squared plus z squared equals 1, which hopefully we should recognize that equation as just being the unit sphere. So we're looking for the volume of that unit sphere. Now, this is a good one where right from the beginning, we could think about converting to probably spherical coordinates. We could do rectangular. To do rectangular, we'd have to go from, again, it's like the one we did last time, where you'd have to go from like the lower hemisphere to the upper hemisphere, and then the cross section of R is going to be, again, that unit circle. So we could go from like the lower semicircle to the upper semicircle. Now, what's kind of interesting when we do spherical coordinates is we're really going to think about all three coordinates more three-dimensionally. Because unlike cylindrical, right, for cylindrical, it's really like a two-dimensional coordinate system that then we just add that third z dimension to. And so we really think about R as being a two-dimensional region and doing R and theta as my coordinates there. But that's not really the case for spherical. Everything in spherical is three-dimensional. So if I picture having some sort of point here, this is what we're going to try and think about, is how does that point need to move around in order to trace out everything within this sphere. So let's try and think about, what does rho need to do, what does phi need to do, and what does theta need to do. And we want to remember, get everything within this sphere. So if we think about it, well, we need to have rho go from the origin all the way to the exterior of the sphere. So we want to get anything along that point so that it's a solid sphere. So we're going to go from rho is 0 all the way over to rho is 1. So that kind of lets that radius kind of like extend, if you will. Then if we think about for phi, remember, is this angle between that little line segment and the z-axis. And if you think about it, well, what we really need is we need to be able to swing the full, we want the full sphere, right, all the way from the upper hemisphere to the lower hemisphere. Now remember, a key thing to remember with phi is we only go 0 to pi. So we're just going to essentially swing upper hemisphere to lower hemisphere, because then what we're going to do is when we think about theta, we're going to let theta swing all the way 0 to 2 pi. So basically what that then lets me do is we would see, all right, I can be anywhere along this radius. I can do kind of like a half hemisphere, and then that whole thing is going to then swing all the way around the z-axis to give me the full sphere. So really, this particular example, we can very much think of geometrically, looking at that three-dimensional geometric picture to see why we want essentially all three of these variables. So what we're going to see then is we just need to put things where they go. So we can do volume, we could do theta on the outside, though it really doesn't matter because they're all constant values. None of them are functions of one another. So we could go from 0 to 2 pi, 0 to pi, 0 to 1. And then remember, if it was rectangular coordinates to find a volume, we would just integrate 1. So because it's spherical coordinates, we need that factors for spherical coordinates, which was the rho squared sine phi. And then what we're gonna end up with from there is we just need these to go in the correct order. So we did d rho, and then we did d phi, and then d theta. So again, we wanted the full, all the way to the center of the sphere, so that was why rho went from 0 to 1. Phi went its full rotation from 0 to pi, and then that was able to swing all the way around from 0 to pi over 2. If we had only done something like phi went from 0 to pi over 2, we would only get the upper half sphere. So it would only swing this far, and then that would swing a full rotation around. If we did something like restrict theta to say only 0 to pi, we would get like half of a sphere where it's sliced vertically in half. So it would be like the sphere that goes from the positive x-axis back to the negative x-axis, to kind of help you picture some of those things. If we did something like rho only went from like 1/2 to 1, then that would be the sphere with the core cut out. So it'd be like a sphere missing a middle. So that kind of helps you maybe visualize what all of those dimensions are going to do. We will do a few examples later where we're actually going to have some functions that will sub in those formulas for like what is x and y and things like that. But it's nice to kind of start with a very visual one just first.